So this is going to be Lab 3, Magnetic Field of a Bar Magnet by Jackson Perreault. So to start with the introduction, the purpose of this lab is to model the magnetic field of a bar magnet. This is done by first experimentally determining the distance dependency of the magnet, then using this value in the Biot-Savart law. This allows us to determine both the magnetic dipole moment as well as the magnetic field of a point that's off axis. Done through the use of Python or the web Python that we use, the web glow script, we are able to determine how accurate these determined values are compared to the computational model. And these fundamental principles that we're going to be using in this lab is the Biot-Savart law as shown in here with the Biot-Savart equation clearly shown. So moving on to assumptions, we have two main assumptions. When the magnetometer is far away from the magnet, it measures a near zero magnetic field in the x direction, as well as the magnetic meter moves closer to the magnet, the magnitude of the measured x component of the magnetic field then increases. So for systems and surroundings, we have the objects involving the earth, magnet, and the phone magnet or the phone. So for initial conditions, everything we have is going to be solved for in the lab. So to start off with the experiment, in this experiment, I used a phone magnetometer to determine the positions of a magnetometer chip and find the absolute values of the magnetic field for an off-axis or for an on-axis point. And then we create a graph based on the values of n and ln of k to solve for magnetic moment. So up in the right corner, we have that plotted graph. And underneath, we have for lab 3 the BX values of 20, 70, 120, 170, and 220 micro-Ts, as well as all of the various points at which we read those values in meters. So 0.31, 0.28, and 0.29 for that first value. And as it goes further down, it generally decreases. We are also given a final y equation of y equals negative 3.3096x minus 14.924. Then for the second part of this experiment, I found similar information, however, along an off-axis. This allows me to determine the net magnetic field to the bar magnet, however, along a different axis, giving me a final B net value of 1.91 e to the negative 8t, as calculated in that bottom green section of this chart, with all of the entered values being experimentally found in this chart shown in the bottom section of it. So for the first part of the code, we establish the magnitude of the magnetic moment in that middle section and create the magnetic field in that second section of the coding. Then we establish all of the observational locations for the two on-axis and four perpendicularly axis positions. Then we also establish the arrows for the on-axis magnetic fields. In the code 3, we establish the size and direction of the off-axis or perpendicular magnetic fields and establish the arrows for them. In this final part of the code, or code 4, we establish a magnetic field 45 degrees of axis, citing both the observational location and specifications for said arrow or said magnetic field, and we also establish several prints. And here we have the final code, or the computer-produced model of my arrows, and its established size and direction of the various forces as displayed by the arrows, as you can see, as well as the printed values in the below section. So we have the experimental magnitude of d equals 1.91 e to the negative 8t as found earlier. However, the model magnitude of b is d equals 1.6948 e to the negative 8t. And the reasons for the discrepancies or differences between computer and experimental models is largely due to the influence of other magnetic fields on testing equipment, as well as human error affecting how precisely we were able to gather data. So for the discussion, what if you had oriented your experiment to compensate for magnetic north and instead laid out your meter stick at some intermediate angle? If you hadn't compensated for north, you would have been unable to solve for the off-axis or perpendicular magnetic fields, as every point would have had a larger magnitude in the x direction due to the magnetic field from the Earth, and therefore would have had a smaller y direction, smaller y directional magnitude, which would have ended up in incorrect results. Now, if we were to stick two identical magnets together end to end and then run the experiment again, so sticking the two identical magnets together, I'm assuming that they'd be both running in the same direction, so north to south and north to south, or south to north, considering it'd be hard to stick them together otherwise, which would result in the magnitude of the magnetic field doubling. Now, for possible error, the possible errors in this lab could have come from the limitations of slight inaccuracies due to other magnetic fields, or largely just based off human error. So for this conclusion, through this lab I furthered my understanding of magnetic dipole moments relating to magnets, and by extension the magnetic fields formed by said magnets, with this final value of B net being shown below. Thank you.